One of you tell me, what is the basic difference between solids and fluids? Basic difference between solids and fluids.
Well, solids have a definite shape, but fluids does not have definite shape.
Good. Solids have a definite shape, fluids do not. Okay. Solids have a definite shape as long as there is no stress applied on them. Once you apply a stress, the shape can change. Correct. Now, fluids include both liquids and gases. Okay. So in this chapter, we are going to discuss some of their properties, how they behave, and how to predict what a system will do. Okay. What a fluid system will do based on the forces acting on it and based on the forces applied by it. Those are the things that we will learn in this chapter. Okay. Consider a liquid, for example. Okay, this is the side view of a container filled with liquid up to a certain extent, certain level. Now, imagine placing a piston over the surface of liquid. Okay, so imagine the entire surface is covered with a piston like this, and you start applying a downward force on the piston. One of you tell me what will happen. We cover the entire liquid surface with a piston and start pressing it down with a certain amount of force. What will happen?
The liquid gets compressed, sir.
Okay, have you ever observed this in real life? When have you ever tried it? Did it happen?
So when we press it, the water comes out.
From where does the water come out?
Sir, if there is a gap between
Okay, if there's any gap, from the gaps it comes out. That's fine. How are you able to say that the water is getting compressed? See, it is escaping. That is fine. How do you know that it is getting compressed?
Sir, its volume decreases.
Have you ever observed that? Actually observed that?
No, sir.
Okay, fine. See, what she said is correct. When we apply a force like this, basically what we are doing is we are applying a force perpendicular to the cross-sectional area. So what we are doing is exerting a longitudinal stress on the liquid surface. Okay. As a result, she said the liquid gets compressed. See, it's hard to observe actually. Liquids are compressible, but not so much that you can easily see the compression happening. To some extent, they are. Okay. If you apply a very large amount of stress, then you'll be able to notice the compression also in case of liquids. In gases, it is more pronounced. Okay. In gases, it is very easy to observe compression. Okay. So, yes, it is possible to compress fluids. Fine. Real fluids are compressible. Solids themselves are compressible. Why not fluids? Okay. At the molecular level, what is the difference between fluids and okay? What is the difference between gases, liquids, and solids? The space between the molecules. In solids, the space is very less. The molecules are tightly packed. In liquids, gases, there is more space between the molecules, right? If there's more free space between the molecules, definitely they are more compressible than solids. So if a solid itself can be compressed, liquids, gases can definitely be compressed. Okay. Now, usually what happens as you compress, the internal forces, the restoring forces will oppose the compression. So it will get compressed to a certain extent and stop. So real fluids are compressible. What does that mean? That doesn't mean you can compress them to zero volume. No, whether it's a liquid or a gas, you can't compress it to zero volume. Okay. As you compress them more and more, the restoring forces will be stronger and stronger. It will become difficult to compress. Okay. So they do oppose longitudinal stress. They do oppose or resist. Okay. Longitudinal stress, but not totally. Okay. So to a certain extent, they do get compressed. After that, they'll be strong enough to oppose. Now, we are going to consider in your syllabus, you only have something called an ideal fluid. An ideal fluid is incompressible. Okay. Real fluids are definitely, see, when solids themselves are compressible, fluids, that is liquids and gases, are definitely compressible. We will assume that fluids are incompressible. Okay. As far as this chapter is concerned, we'll assume that way. Next chapter onwards, again, thermodynamics and all, there we will consider the compression of gases. Okay. So especially liquids, we'll assume they are incompressible. So an ideal fluid is incompressible. What does that mean? They can oppose any amount of longitudinal stress. Okay. Or they can resist any amount of longitudinal stress. So you apply stress, you will not be able to observe any deformation, means you will not be able to observe any strain. So whether stress is small or, I mean, whether stress is less or high, doesn't matter. Okay. High or low doesn't matter. Strain will be zero. Okay. No longitudinal strain at all. Fine. Obviously, there will be no bulk strain also. Okay. Longitudinal means only length increases or decreases. Bulk strain means entire volume. That also ideal fluid will resist completely. You cannot compress an ideal fluid. Okay. So basically, ideal fluids are incompressible. See, liquids, we'll assume they are absolutely incompressible. In engineering, you will learn how to include the compressibility factor of liquids. Okay. For now, you don't have to bother about it. Fine. Then, okay, let's consider this liquid container itself. What if we break this wall? Okay. Happen to the liquid? Normally, from your everyday experience, you tell. If you create a hole in the wall or if you break the wall of the container, what will happen?
So the liquid will flow out.
Liquid will flow out. Why are the others hesitating to say that? The liquid will flow out. You can imagine it like this. Okay, it depends on the space that you provide. Fine. So basically, when the liquid flows out like this, can any of you tell me what makes the liquid flow out? Why does it have to flow out? What force is pulling it?
So the wall restricts the water from flowing out. So when the wall is removed, the water is free
Okay.
to
So you are saying naturally water has a tendency to flow away. Wall was stopping it. Okay, wall was on the right side and left. I mean, lateral walls are there. Okay. Then what was stopping the water from going off like this?
gravity.
Okay. Here also, it is gravity that pulls the water down. Otherwise, it could have gone in any random direction. Why does it flow down? Because of gravity. Okay. So now you can think of it like this. When liquid flows out like this, basically what is happening is the layers of liquid are sliding over each other. Okay. You can just imagine it like layers falling off. So fluid layers can very easily slide over each other. That is what flow means. Flow implies sliding of layers over one another. Okay, that is what flow is basically. In solids, it does not happen. In fluids, it happens. And in case of real fluids, there will be some resistance to flow. You all must be aware of something called viscosity. Okay, some fluids are thicker than other fluids for in terms of flow. For example, water can flow relatively easier compared to honey or gum. Okay, so different fluids show different kinds of or different amounts of resistance to flow. Some fluids are very free flowing. Some fluids are not that easy to make them flow. Okay, so real fluids exhibit something called viscosity. What is viscosity? Okay, so real fluids are viscous. Now, initially, we are going to consider ideal fluids. Ideal fluids are assumed to be completely non-viscous. Okay, so we are not going to consider viscosity as of now. So ideal fluids are incompressible, means they can resist any amount of longitudinal stress. Now, how to resist longitudinal stress? See, longitudinal stress is created by forces perpendicular to the walls, okay, or cross section. If the liquid is resisting it, that means, and not just like this, from everyday experience, you can tell the liquid molecules will be pushing the walls of the container also. The moment you make a hole, the liquid flows out. Means before making a hole, the liquid would have been exerting forces on the walls of the container. So there will be forces acting like this also on the lateral walls. There will be forces acting on the base of the container also. Okay, we can experience these in real life. If you make a hole in the wall and you want to stop the flow of liquid, you will have to press against that hole to prevent liquid from leaking out. Because liquid will be exerting a force, you will have to overcome that force. So basically what you need to understand from this is that ideal fluids can exert forces perpendicular to the surface with which they are in contact. Okay, they can exert forces perpendicular to the surface of contact. But see, fluids are called fluids because they flow. Flowing means what? Layers sliding over each other. An ideal fluid is absolutely non-viscous, means there is no resistance to flow at all. One layer can easily slide over another layer without any resistance. One layer sliding over another layer without resistance means what? No friction between them. No friction between them means what? The layers cannot exert, or an ideal fluid cannot exert a force parallel to the surface. Okay, anything can easily slide over the surface of a fluid. Okay, or reverse, a fluid can easily slide over any surface. An ideal fluid can completely freely slide over any surface. So what does that mean? Ideal fluids cannot resist a tangential stress. So tangential stress makes layers move over each other. A solid can oppose that up after a certain extent. It will undergo a little bit of deformation, and then the restoring forces won't allow the layers to slide anymore. A liquid or a gas cannot do that. Okay, an ideal fluid can absolutely not do that. It cannot oppose layers from sliding over each other. Okay, so ideal fluids cannot resist a tangential stress at all. Fine. What does that mean? That means they cannot surface of contact. These are very important properties, ideas. Okay, so fluids can exert forces perpendicular to the surface of contact, but they cannot exert any force parallel to the surface of contact as far as an ideal fluid is concerned. Real fluids exhibit viscosity. We will study viscosity towards the end of the chapter. For now, we will only be dealing with ideal fluids. Okay. Right. So let's summarize the idea of an ideal fluid. First is that it is incompressible. Any amount of resistance to a longitudinal stress means absolutely free flowing. That means they cannot offer any resistance to a tangential stress. Okay. It also means that the fluid can exert force perpendicular to the surface of contact. Ideal fluid being non-viscous means they cannot exert any force parallel to the surface of contact. Okay. This will help us in determining what happens to a fluid system. Okay. Okay. Can one of you quickly tell me the formula for Young's modulus? Or bulk modulus, you tell. Okay, not Young's modulus, bulk modulus.
Minus del P by del.
Okay. And what is the definition? By definition, what is bulk modulus? The formula you said is correct. Volumetric stress divided by volumetric strain. Okay. Now, we just discussed the properties of an ideal fluid, and I told you that ideal fluids are incompressible. Means you can try to compress them, but you won't notice any compression happening. So based on that property, you all find out what is the bulk modulus of an ideal fluid. based on the fact that they are incompressible. Irrespective of how much ever stress you apply, you won't notice any strain. Okay. Based on that, you tell me how much is the bulk modulus of an ideal fluid. I'll give you all 1 minute. Type your answers in chat. Fine. Now, basically, you can apply any amount of stress. So numerator can be non-zero. Denominator will be 0. Actually, non-zero by 0 is undefined. But in physics or generally in science, we say this tends to 0. Okay. Some non-zero number divided by a number which is tending to 0, the result tends to infinity. Okay. So bulk modulus of an ideal fluid tends to infinity. I mean, this is how you are supposed to say it. Remember, modulus of elasticity, whether it's Young's modulus, shear modulus, or bulk modulus, tells you how difficult it is to deform that material. Okay. So bulk modulus of an ideal fluid being infinite means it is infinitely difficult to compress an ideal fluid. Okay, and that is what we discussed about ideal fluids. They are incompressible. So that's why the bulk modulus is infinity, or tends to infinity, you can say. Okay, next. Can one of you tell me the basic definition of shear modulus? Shear modulus or rigidity modulus, which we denoted by the symbol G. What is it by definition? Okay, it's basically shear stress divided by shear strain. Now, in case of an ideal fluid, as I said, the layers of fluid flow freely over each other. There is no resistance. An ideal fluid cannot exert force parallel to a surface of contact. If it cannot exert force parallel to a surface of contact, the stress will be tending to 0. Okay. Like, you simply cannot exert a significant amount of force parallel to the surface of a fluid. That is what it means. And if you cannot exert force parallel to surface, that means the stress tends to 0. If stress tends to 0, or okay, stress tends to 0, that's fine. But deformation will happen freely. The layers will slide over each other freely. They are sliding over each other means deformation is happening. Strain is there. And you can get any amount of strain. Strain is a non-zero value, you can say. Stress tends to 0. Strain is a non-zero value. Fluids do get deformed. Okay, fluid layers can slide over each other. So shear strain will be there, but stress will not be there. So shear modulus G tends to 0 for an ideal fluid, not for real fluids. Real fluids can exert a little bit of force parallel to the surface also. Ideal fluid cannot. Okay. So bulk modulus of an ideal fluid tends to infinity because it is incompressible. Shear modulus of an ideal fluid tends to 0 because it is free flowing. Okay. Right. Now, see, we have gone through mechanics of solids, right? Starting from loss of motion, then work energy, power, system of particles, gravitation, all these chapters. Whenever you are given a problem in mechanics and you are asked acceleration or velocity or whatever it is, what is the first thing we think of? To determine what happens to a system in mechanics, what is the first thing we consider? How do we start solving any problem? Suppose you are given a system, let's say blocks connected by threads, and I ask you what is the acceleration or how much speed a block will gain after some time. How do you start solving the problem? The first thing we consider is the forces acting on the system. Okay, based on forces, we write equations, right? The behavior of a system depends on the forces acting on it. And what happens to the surroundings depends on the forces exerted by it. Okay, fine. Now, in mechanics, the force, like in mechanics of solids, the forces we used to consider were normal force, friction, weight, tension, these things. In case of fluids also, it is almost the same. but the way we express the force is different. Okay, because the main difference between solids and fluids is that fluids can flow, means they can exert forces horizontally also. Okay, like the liquid in this container, it wants to escape, it will be exerting a force on the wall. Instead of liquid, suppose you put a block in the container, the block will not exert a force on the walls of the container. No, block will only exert force on the base of the container. Why will it push the walls? It won't, unless it is tightly fit, it won't. But liquid will be pushing the walls. Okay, so flow is the basic difference between solids and liquids. And if you want to deal with liquid systems, you should know how to express the force they exert. Right? Like this liquid, the liquid in this container that you see, will be exerting a force on its walls. Okay, you can call it normal force because the force is perpendicular to the wall. You can call it a normal force, that's fine. But how to write an expression for it? Okay, so in order to express the force exerted by a fluid, you first need to understand how to calculate pressure in the fluid. Okay, fluids exert force by means of pressure. Okay, pressure basically makes the molecules want to escape from that place. Greater the pressure, greater their tendency to escape from there. So greater the forces they will exert. So the force exerted by a fluid depends on the pressure of the fluid. So the first thing you need to know if you want to deal with fluid systems is how to calculate pressure in a fluid. So we'll first talk about liquids. Fluids include both liquids and gases, but for now we will deal with liquids. We'll be talking more about gases in the next chapter, thermodynamics actually. Okay, let's consider liquids for now. Again, let's consider this container itself, which is filled with liquid up to a certain extent. Can one of you tell me the basic formula for pressure that you know? Like by definition, what is pressure? Fine. Pressure on a surface is the force acting perpendicular to the surface per unit area. Perpendicular force divided by area. Or you can also write it as small amount of force acting perpendicular divided by small area. Okay. Now, force is a vector quantity. It comes with a direction. But pressure, by definition, is a scalar. So when we write perpendicular force, you are area. Don't include its direction. Force has direction. Pressure does not have direction. Okay. By definition, pressure is a scalar quantity. On the basis of pressure, you can tell the direction of force, but never say pressure acts in a particular direction. No. Due to pressure, force acts in a particular direction, that you can say. Okay. Note on this formula, all of you, P is equal to F perpendicular divided by A. Force acting perpendicular to a surface per unit area. Okay. Now, obviously, since it's force per unit area, the SI unit of pressure will be Newton per meter square, which is commonly called as Pascal. I hope you all know this. When it's the name of a scientist, see, this is the unit that we are referring to. It's named after a scientist. Okay. But if you're writing the full word, it has to start with a small letter. It's a rule. Okay. The symbol can start with a capital letter as given in the SI system. But if you're writing the full word of the unit, full name of the unit, it has to be written in small letters only. Okay. It's a rule actually. Fine. Can any of you tell me some other commonly used units of pressure? Pascal is the SI unit. What are the other common units of pressure? How much is atmospheric pressure? Anyone? How much is atmospheric pressure? right? In India, usually when you get the tires of a vehicle filled, the pressure is expressed in terms of PSI. Pound is a unit of force. Okay, it's actually weight. British people, they measure weight in pounds. You all must have heard of that unit at least. So PSI is basically pound per force, square inch being the unit of area. Okay, bar is another unit, and atmospheric pressure is expressed in atmospheres itself. Okay, let us discuss this a little bit. To the power of 5 pascals. Okay, it's a significantly large amount of pressure. 1.01 in 10 power 5 pascals. What does that mean? It means 1.01 into 10 power 5 newtons of force per 1 meter square area. Okay. Now 1 into 10 power 5 newtons of force basically is the weight of 10,000 kgs. So you imagine putting 10,000 kgs over an area of 1 meter square. The pressure it creates is 1 pascal. It's a huge amount of pressure. And we are all experiencing that pressure all the time. Okay, that is what is atmospheric pressure. How does atmospheric pressure arise? What is in the atmosphere? Air basically, which is gas. Okay, gas molecules at temperature greater than 0 Kelvin. Okay, gas molecules will always be moving around randomly. They cannot be at rest. If they are at rest, that means temperature is 0. We'll talk about this in the next chapter, thermodynamics. It's called absolute 0 of temperature. If a gas is completely at rest, it means the temperature is 0. If temperature is non-zero, on the Kelvin scale, gas molecules will be moving around. Same thing happens with air also, air or any gas. So these gas molecules, when they move around, they'll be striking walls of the container or whatever object they come into contact with. Okay. Whenever gas molecules strike an object, they create pressure on it. They exert pressure on it. So that pressure created by air molecules surrounding us is what we call atmospheric pressure. Okay. We are all compressed under that pressure. If atmospheric pressure had not been there, our bodies will explode. Okay. I think it's the lungs or blood vessels will get ruptured. The blood cannot stay inside the body if that pressure from outside is not there. That is why astronauts have to wear space suits. Okay. Space suits ensure that the body of the astronaut is under pressure. Because in space, like once you go out of Earth's atmosphere, there's no atmosphere, there's no atmospheric pressure. And if there's no atmospheric pressure, that external pressure on us is not there, what will happen? Due to the blood pressure inside, the blood vessels will get ruptured and you know what will happen. Okay, I don't want to describe. So it's not safe for us. Okay, we have to be under that pressure to survive. We have evolved like that. Fine. So just remember that atmospheric pressure is a huge amount of pressure, not something that you can ignore. Okay, there are some very interesting experiments also based on atmospheric pressure, just to help you understand how significant atmospheric pressure is. Okay, I'll share them with you later. So in gases, that is how pressure arises. Gas molecules are always moving around randomly. They don't even have a particular direction of motion. It's not like they want to go down because of gravity. Gas goes against gravity also. Okay, you open a container, gas will escape. Liquid cannot do that. Liquid cannot go against gravity on its own, but gas can go. Okay, that is because gas molecules are moving around randomly. So that is why how you calculate pressure exerted by a gas is different from how you calculate pressure exerted by a liquid. So for now, we'll stick to liquid, but we will have to consider atmospheric pressure in our calculations because everything around us. Right. So how a gas exerts pressure is different from how a liquid exerts pressure. So for now, we will stick to liquids. And remember that atmospheric pressure is a huge amount of pressure, 1.01 into 10 power 5 pascals. And this is what we call as 1 atmosphere. Okay, so atmosphere is itself a unit of pressure. And it is equivalent to almost close to 10 power 5 pascals. Okay. And there are some other slightly confusing units of pressure also. 1 atmosphere is close to 76 centimeters of mercury. Okay. Atmospheric pressure can be expressed as the length of a mercury column also. You'll understand how this can be done. Some of you may be knowing it already. There's an instrument called a barometer, which helps us express pressure in terms of length of a liquid column. We'll discuss this later. So Pascal, atmosphere, centimeters of mercury. These are the common units that we are going to come across. Okay. So let's see how to calculate pressure in a liquid. Because if you know pressure in a liquid, then you can tell how much force the liquid will exert. Okay. So assume there is a static liquid. Can any of you tell me what static means? Or what is the meaning of a static liquid?
So there's no flow of the liquid.
There's no flow, correct. Okay. There's no movement at all. So what does a static liquid mean? The liquid is at rest. With respect to the container in which it is present. Fine. It's not moving and it does not move also. Under that condition, we will derive an expression for pressure in a liquid. Okay. So let's say the liquid is static, and let's consider one more condition also. First case, container is not accelerated. So container, assume the container is at equilibrium. You'll understand why this matters. So for now, we will only be dealing with static fluids, static liquids to be precise. And let's consider a case where the container is at equilibrium. Now, if container is not accelerated with respect to ground, okay, container is not accelerated and the liquid is at rest with respect to container, it means the liquid is also not accelerated. Okay. So the entire liquid is at equilibrium or in equilibrium, both with respect to container and also with respect to ground. Okay, let's consider that situation. Assume the liquid has a density rho. Which is basically mass per unit volume. Assume the density is rho. Now we are assuming incompressible fluids, okay, ideal fluids. If it is incompressible, it means the density will be same everywhere. You exert any amount of pressure, it's not going to shrink. So volume is not going to change, so the density will not change. So we are considering a fluid which has the same density throughout. Okay, a liquid which has the same density throughout. Fine. Now, from common experience, we all know that as we go deeper into a liquid, the pressure increases. Okay, you all must have heard this. Recently, there was this deep sea exploration pod. What is the name? Titan. Have any of you heard about Titan?
So the one which the 5 million is dying.
Yes. The name is Titan itself. No, what was it?
There's something with Titanic only, rhymes with the Titanic.
Just a moment. Let me check. Yeah. So basically, it's a pod. What is a pod? It's a closed shell. You can imagine it like a closed shell made of very strong metal, actually. I'll download an image. Just a moment. Yeah. So there was, I think there was only, I don't think that company exists anymore. So there was this company called Ocean Gate. Okay. They do deep sea tourism. Okay. They take people deep under the sea. So the name of this particular ship or pod is Titan. So what happened? They went deep into the ocean, but at one point, at a certain depth, what happened is the pod imploded. Imploded means what? Getting crushed from outside. Okay. Why did that happen? Because the pressure around it was so high. They went so deep into the sea that the pressure was unbearable for that material. Okay. So the material got crushed. And of course, the people inside it also got crushed. All 5 of them died. Okay. So it is known from experience that as we go deeper into a liquid, okay, in this case, the water in the sea, as we go deeper into a liquid, pressure increases. Fine. So we will first derive an expression for pressure in a liquid at a certain depth. Now you need to first understand that this is an open container. A container which is open to atmosphere will already be under atmospheric pressure. These air molecules which are outside this container, they'll be hitting the surface of water, surface of liquid. Okay. So the liquid surface is already under atmospheric pressure. Atmospheric pressure is usually denoted by the symbol P naught. Okay. So remember, P naught stands for atmospheric pressure. Right. So the upper surface of water, the free surface of water is already under some pressure. Fine. Now what we want is an expression for pressure at a certain depth inside. Let's consider a point somewhere here, which is at a depth h. From where? From the free surface. Okay. At that point, we want an expression for the pressure. Now, the only formula we know for pressure is that pressure is force per unit area, perpendicular force acting per unit area. Now, if you want the pressure at this point, you need to imagine a surface first. And you have to calculate how much force acts on that surface. Based on that, you can tell what is the pressure. Now, how do we imagine a surface? Now, we want pressure in terms of depth, right? As you go deeper into a liquid, you want to find out how the pressure varies. So what you have to do is, see, pressure is perpendicular force per unit area. So you have to take an area and then calculate force perpendicular to that area. Now, the only force we can calculate on the liquid is its weight. We don't know anything else about liquids as of now. Okay, about fluids, we don't know anything else. Only thing we can calculate is the weight. Okay, so what we are going to do is we are going to take a cross-sectional area like this. Okay, now you can't simply take a cross-section and write force on it. No, some weight or something should be there on it. Okay, so what we are going to do is we will take a cylindrical part of this fluid. See, we are not immersing a cylinder into this liquid. The liquid is there already. We are considering a part of that liquid which is in the shape of a cylinder. We call it as a cylindrical element actually. It should be a very thin cylinder, but for our understanding, I'm showing it as a thick cylinder. So consider a cylindrical element of the liquid. Now, why did I take only a cylindrical element? Why not some other shape? I could have taken a cuboid cube also. Okay. But random shapes have to be avoided because calculation becomes difficult. Now, if you consider a part of this liquid which is in the shape of a cylinder, now the liquid is in equilibrium, right? So this cylindrical volume is also in equilibrium. Equilibrium means what? Net force 0. Okay. The upper surface is open to atmosphere. Atmospheric pressure is acting on it. Air molecules will be striking it, no? So there is a force acting on the upper surface already. That is the force due to atmospheric pressure. How do you calculate force due to pressure? Now pressure is perpendicular force per unit area, no? Then if pressure is perpendicular force per unit area, then the force acting perpendicular to an area will be pressure multiplied with that area. Simple. Okay. So that upper surface is under atmospheric pressure P naught. Let's consider the area as dA. Small area of cross section I'm taking. You can take it as A also, no problem. But just to make you understand that it's a small area, I'm writing it as dA. Pressure is P naught. Area is dA. Okay, same area here also. Upper surface also has the same area dA. Can one of you tell me how much is the force exerted on it by atmospheric pressure? If the pressure is P naught and the area on which it is acting is dA, how much is the force acting on it?
P naught into dA.
P naught into dA, correct. So a force of P naught dA will be acting downwards due to atmospheric pressure on this cylindrical volume. Okay, see, air molecules will exert this atmospheric pressure wherever they strike. Fine. On any surface which is open to atmosphere, that pressure will be there. So you can find out the force acting on that surface if you know its area. Pressure into area gives you the force. Okay. What other forces act on this volume of the liquid? The volume that we have highlighted here. Can any of you tell me what other forces act on it?
Sir, mg downward.
Weight will definitely be acting. Correct. Correct. Its weight will be acting this way. Okay. Now weight, usually in solids we write it as mg. When it comes to liquids, we express weight in a slightly different manner. We have considered liquid's density as rho. Okay. Now this is some random volume that we considered. Let's say the volume is V. Okay. Or since it's the thin cylindrical element, you can call the volume as dV. Let the volume of cylindrical element be dV. You can call it V also, no problem. Since it's a very small volume, I'm writing it as dV. Okay. Now we know density is mass by volume. So small mass divided by small volume becomes density. Therefore, mass becomes density multiplied with volume. This is how we express masses of fluids. Okay, we express it in terms of their density. Okay, so weight mg will be acting on it. How do you express that? It's a small mass multiplied with acceleration due to gravity. So we write it as rho into dv. That is small mass multiplied with g. If you take volume as V, you can write it as rho Vg also. I'm writing it as rho dV into G. That is how we express weight. Okay. So force due to atmospheric pressure is acting on it. Its own weight is acting on it. But we know this part of the liquid is in equilibrium. Equilibrium means net force should be 0. Force due to atmospheric pressure is downwards. Its own weight is also pulling it downwards. How can that liquid stay in equilibrium? Can any of you guess any additional forces acting on it? Additional forces acting on it. What other forces act on this part of the liquid? Okay. See, this volume is surrounded by liquid, right? Now you imagine if we make a hole in the container here, liquid will flow out from there. That means liquid is pushing the wall of the container, right? Wherever the liquid is in touch with something, is in contact with something, it will be pushing it. So the liquid here is pushing the wall of the container. Similarly, the liquid surrounding this cylindrical volume will be pushing this cylinder inwards. Okay, we'll be exerting a force inwards on this cylinder like this. From below also, there will be forces acting. So from all sides, there will be forces acting on this cylindrical volume perpendicular to its walls. Fine. Surrounding liquid will be exerting this force. Now from the sides, there is force that is understandable because you know that if we make a hole in the wall, liquid will flow to the side. But liquid never flows upwards, not automatically on its own. then how do we explain these forces acting on the base? Basically, you imagine, you can explain it by imagination. Suppose there's a container like this, a U-shaped tube. Okay. You fill it with liquid up to a certain height on both sides. Okay. Now one of you tell me, or all of you also can tell, if we make a hole here, will liquid flow out or not? The system is under gravity, like it's placed on a table. Consider gravity and all. If we make a hole as shown, will liquid flow out of that hole or not? What do you
No,
think?
sir.
Okay, somebody is saying no. Then I have another question for those of you who are saying no. Does that mean this wall is useless? Can we just keep it open like this?
So would it flow out if the pressure is applied on the top columns?
We are not applying any pressure. Okay. There is a U-shaped tube like this. Okay. Filled with liquid, as you can see. If we make a hole as shown, or if we create a gap here, will liquid rise up through that gap or not is what I'm asking.
Yes, sir.
It will definitely rise up. If you want, you all can try this also. You take a paper cup or a plastic cup. Okay. Take a paper cup or plastic cup, make a hole in its base, small hole. Not very small, because if it is too small a hole, then the effects of surface tension may prevent the water from rising up through that hole. Okay, so make a hole which is a few millimeters in diameter. Okay, something which you can cover with your finger. Okay, you should be able to close the hole with your finger. Okay, so make a hole like that in the base of that plastic cup. Immerse it into a bucket of water. Immerse it into a bucket of water and then remove your finger. You will see that water will get into the cup from here. Definitely it will. Okay. What does that mean? That means before the hole was opened, there was force acting on it. There must have been force acting on it. The moment you open the hole, water is coming in, means water was already pushing it. Okay. Same thing happens here also. There will be force on the base of this cylindrical volume that we have considered. Okay. Now, how do we express that force? See, there are forces from the sides. Forces from the sides will cancel. There is force from the right side, there is force from the left side. They'll cancel. But force from the base or force on the base, there's nothing to directly cancel it. So you need to include that in the force expression. Now, the force that is acting from below can only be expressed in one way. Let's say the pressure at this level is P. Okay, pressure at a depth H, let it be P, and the area is dA, then the force acting on that area, on the base, will be P into dA. On the upper surface, it is P naught into dA, atmospheric pressure multiplied with area. On the lower surface, it will be P multiplied with dA. Pressure at that level multiplied with the area. Okay, so now if you only consider that cylindrical element, what all forces act on it? One is its weight, for which we have written an expression. One is the force due to atmospheric pressure, which acts downwards, and the other is the force from below. Who is exerting that force from below? Whatever liquid is there below it is exerting it. Okay. Under the influence of these three forces, one of them is P naught into dA, the other is its weight. Weight expression we have written density into volume, that is mass, multiplied with gravity. Okay, mg, that is weight. The other force is pressure P multiplied with the area on the base, area of the base, which is PdA. There will be no other forces acting on it. The forces from the sides, they get cancelled. Even if they don't get cancelled, for vertical equilibrium, you don't have to include those forces. Okay. And here, another property comes into picture. We assumed ideal fluids to be non-viscous. Okay. Ideal fluids are non-viscous. What does that mean? They cannot exert a force parallel to a surface. Okay. Parallel to a surface of contact. That also has to be considered here. On the side walls of this cylinder, we are not considering any upward force or downward force because we are considering an ideal fluid. Ideal fluids do not exert forces parallel to surfaces. Okay, they only exert forces perpendicular to surfaces. So from the left side and right side, there will be forces, but up and down, there won't be any forces on the side walls of the cylinder. On the base, it will be there. Obviously, perpendicular to base means upwards. That force will be there. Perpendicular force will be there. Parallel force won't be there. Okay. Now, under the influence of these three forces, that part of the liquid is in equilibrium. So, liquid is in equilibrium with respect to ground. Okay. See, with respect to container, it is anyway in equilibrium. Static liquid we are considering. Container itself was assumed to be non-accelerated. Okay. Container itself is at equilibrium, non-accelerated. Therefore, the entire liquid is in equilibrium with respect to ground. So, these forces must balance. So, the sum of downward forces should be equal to the sum of upward forces acting on it. This will help us derive an expression for pressure P. So, you can write pressure P is equal to, what is P? Pressure at a depth below the free surface. That is what we are trying to derive. Pressure at a depth below the free surface becomes P naught dA plus density into volume into G divided by dA. Okay. The volume of the liquid that we considered here can be expressed like this. The height was h, right? And the cross-sectional area was dA. It's a cylindrical volume. So the volume can be written as h multiplied with dA. Okay. Area of cross-section into height. That becomes volume. Now dA gets cancelled. And you will be left with P is equal to P naught plus rho G H. Okay. Very important and useful equation in this chapter. So what have we derived? In case of a non-accelerated static fluid, we have derived an expression for pressure at a depth h below its free surface. Okay. Surface was under pressure P naught. This is surface pressure. And if you go deeper by h into the liquid, the extra pressure, extra pressure will be rho GH. Okay. So this part rho GH, the extra pressure is called gauge pressure. Some call it as gauge pressure also, that's fine. Okay. The whole thing is called absolute pressure. Only rho GH is called gauge pressure. Okay. But usually while solving problems, we will be interested in the absolute pressure itself because that is what helps us calculate the force. So understand what this equation suggests. P is equal to P naught plus rho GH. P naught is the pressure of the free surface. So if you know the pressure at the surface and you know that the fluid is static and the container is not accelerated, then at a depth h below it, you can tell how much is the pressure. It will be surface pressure plus an extra rho GH. So as the depth h increases, as you go deeper into a liquid, the absolute pressure of the liquid also increases. Fine. There are some other factors on which it depends: density, gravity. Assuming they are uniform, pressure varies linearly with depth. You can even draw a graph for this. P is equal to P naught plus rho GH. So if you take pressure on the y-axis, P naught is atmospheric pressure. It's a constant. Rho and G are also constants. Density of liquid and gravity, they are constants. Height you take on x-axis. So it's like y is equal to mx plus c. which represents a straight line. So we are taking pressure on the y-axis and height on the, not height actually, it's depth from the free surface on the x-axis. Then if you draw a graph, okay, from exam point of view, this is important. Any equation you see, you should be able to plot a graph of that equation. So on x-axis, you take depth, which is h, and on y-axis, you write the, or you consider the pressure, P. When depth is 0, means when you are at the free surface, there is already some pressure P naught. Okay. At free surface itself, there is some pressure P naught. And as depth increases, the pressure increases linearly. So P naught plus rho GH. The graph goes like this. Sorry. The equation is P naught plus rho GH. So they may even ask you questions like this. What is the slope of the pressure depth graph? Okay. So slope here, now height was taken on the x-axis. Whatever is the coefficient of x is the slope. So rho g becomes the slope. Density of liquid multiplied with gravity. Okay. Can any of you quickly tell me how much is the density of water in SI units? This is also something which we are going to use very frequently in this chapter. Okay. Any rough idea you have? Like a 1 liter bottle of water, how much does it weigh? Okay. Density of water is 1 gram per cubic centimeter. Now gram is 10 power minus 3 kilograms. Okay, 1 by 1000 kilograms. And cubic centimeter is like milliliter. 1 cc is same as 1 ml. Okay. Then 1000 cc becomes 1000 ml. That is basically 1 liter. So 1000 cc is 1 liter, means 1 cc will be 1 by 1000 liters. That means 10 power minus 3 liters. Cancel these. The density of water is exactly, pure water is exactly 1 kg per liter. What does that mean? A 1 liter bottle of water weighs exactly 1 kg, excluding the weight of the bottle itself. Okay. 1 liter of water weighs 1 kg. Okay. But still, none of these are SI units. In SI units, mass is expressed in kilograms only, but liter, SI unit of volume is meter cube. Okay. 1 meter cube is 1000 liters. Means you make a tank which is 1 meter by 1 meter by 1 meter. You can fill 1000 liters in it. Okay. If 1000 liters is 1 meter cube, that means 1 by 1000 liters. Wait. 1 by 1000 meter cube will be 1 liter. Okay. So 1 liter is basically 1 by 1000 meter cube. 1000 goes to numerator. The density of water is 1000 kg per meter cube. It's a significantly large density. Okay. Of course, there are objects or materials which are many times denser than water also. But just remember, water's density is quite significant. Okay. Now, why am I talking about density? Because if you know density, you can estimate pressure. Fine, at a depth. So just a moment, let me give you one question. Just 2-3 minutes, we'll close this session. Okay, I just checked for the depth at which that submersible pod Titan imploded, and they have given that it imploded at a depth of around 3,500 meters below sea level. Okay, so from the free surface of water, from the free surface of sea water, at a depth of 3,500 meters, it imploded. Means the pressure became unbearable for that submersible. Okay. Let's consider 3000 meters just for convenience. Okay. So tell me, calculate this all of you. How much is the pressure at a depth of 3000 meters below sea level. Density of water is given to you as 1000 kg per meter cube. Acceleration due to gravity, take it as 10 meters per second square. And atmospheric pressure, take it as 10 power 5 pascals exactly. Okay, it's actually 1.01 into 10 power 5, but many times we approximate it to 10 power 5 itself. So tell me the pressure at a depth of 3000 meters. Calculate this quickly. No response. Pawan, tell me the formula.
Sir, P is equals to P naught plus rho GH.
Okay, so P becomes P naught is 10 power 5, rho is 10 power 3, G is 10, and the depth you are asked to consider is 3000 meters. So we have taken all of them in SI units. So that becomes 10 power 5 plus 3 into 10 power 7 pascals. Now, compared to 3 into 10 power 7, 10 power 5 is a very small number. Or you can write it this way. 10 power 5 can be taken as 0.01 into 10 power 7. Plus there is another 3 into 10 power 7. Effectively, the answer will be 3.01 into 10 power 7. It's okay even if you just write it as 3 into 10 power 7 pascals. But understand how high a pressure this is. Okay. Atmospheric pressure is 10 power 5 pascals. This is 300 times of that. Okay. So extremely high pressure, and that submersible, don't know what material it was made of, but it was unable to bear that pressure. It's not just the material, it's the shape also that matters. Okay, like you all must have experienced this in daily life also. A flat sheet of steel is easy to break, but if you make a ball of steel, okay, hollow ball only, it won't be that easy to break. You all must have heard of eggs, okay, chicken eggs. In one particular direction, if you try to squeeze them, no, it's very hard to break an egg. In a perpendicular direction, it's easy to break. Okay, you look up on YouTube if you want later. So eggs can bear a lot of pressure in one particular direction, in another direction they cannot. So it's not just the material with which the pod is made that matters, the design also matters. So somehow it was not able to withstand that pressure. But anyway, it's not the pod that we should be interested in. You should understand how to calculate pressure at a certain depth. Okay, let's quickly revise what all we discussed today.